Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, thermal expansion and Lindemann melting formula under paper solid state physics. So students, let us see what we are going to learn in this module. Learn about the one-dimensional model to explain the expansion of the solid. Know that the crystal expands as the temperature increases. We will also be able to learn to derive expressions for the Lindemann formula and to know that melting occurs when the lattice vibrations is too long. So while dealing with lattice vibrations, we had approximated the interatomic potential in a crystal by this expression. You see that the first part is the stable equilibrium potential, plus the other higher order terms are the first one being the harmonic terms, then you have the cubic and fourth power and so on, the higher terms. But if we just keep the first two terms, that is the stable one plus the perturbation term, that is the harmonic term, then this is referred to as the harmonic approximation, which was used with much success to discuss the lattice vibrations. However, there are a number of physical phenomena such as A. Thermal expansion, B. Melting of solids, C. Thermal conductivity, D. Temperature dependence of elastic constants, which cannot be explained on the basis of harmonic approximation. The reason of the inability of the harmonic approximation in explaining the above mentioned phenomena lies in the fact that it is not always true that the vibrations of atoms can be treated as small oscillations, and the potential cannot always be approximated by the quadratic terms alone. So the figure that you will see for the harmonic and the anharmonic potential, it will makes it very clear, this thing. So in this particular figure, actually it basically clearly shows the actual potential felt by one atom, and the corresponding harmonic approximation is shown for comparison. So clearly, as the interatomic separation increases, the harmonic approximation breaks down. The validity of harmonic approximation is questionable at high temperatures, where the amplitude of atomic vibrations is so large. So as examples of anharmonic effects, we now in our next two sections deal with the thermal expansion and melting of solids. Thermal expansion. We now give a simple one-dimensional model to explain the expansion of solids. We can write the distance between two atoms, Rx, is equal to Rx naught plus delta Rx, where Rx naught is the equilibrium separation between the two atoms, and delta Rx, which is Rx minus Rx naught, is the deviation from equilibrium. In this situation, we can model the one-dimensional potential shown in the previous figure as V of Rx is equal to V Rx naught plus some constant C delta Rx square minus a constant G multiplied by delta Rx cube minus a constant F multiplied by delta Rx raised to power 4. Here the constants G and F are positive. The term delta Rx equal to 0 is the usual harmonic component. The asymmetry in the potential around delta Rx equal to 0 is accounted for by the term G delta Rx cube. When delta Rx is negative, minus G into delta Rx cube is positive and hence makes the short range repulsion larger. When Rx is positive, minus G delta Rx cube is negative and hence makes the interatomic repulsion smaller for large Rx. The term F delta Rx raised to power 4 represents the softening of the vibration at large amplitudes. We now move ahead and evaluate the expectation value of delta Rx as a function of the temperature T. So delta Rx average is equal to integration from minus infinity to infinity d delta Rx into delta Rx into e raised to power minus beta V divided by integration from minus infinity to infinity d delta Rx e raised to power minus beta V. Now taking into account the expression for the potential, we find that e raised to power minus beta V approximately can be written as e raised to power minus beta multiplied by V, a function of Rx naught, plus C delta Rx square. This entire thing now multiplied by 1 plus beta G delta Rx cube plus beta F delta Rx 4. We now evaluate the integrals in the numerator and denominator of the average value of delta Rx as follows. So first we evaluate the integration from minus infinity to infinity d delta Rx e raised to power minus beta V, which now can be written approximately like e raised to power minus beta V as a function of Rx naught multiplied by the integration from limit minus infinity to infinity d delta Rx into e raised to power minus beta C delta Rx square multiplied by 1 plus beta G delta Rx square plus beta F delta Rx raised to power 4. The odd function, that is beta G delta Rx cube, vanishes, while the contribution of beta F delta Rx raised to power 4 is negligible. Hence, the integration of minus infinity to infinity d delta Rx into e raised to power minus beta V is approximately equal to e raised to power minus beta V as a function of Rx naught whole multiplied by pi divided by beta C whole under root. Similarly, the integration from minus infinity to infinity d delta Rx into e raised to power minus beta V is equal to e raised to power minus beta V as a function of Rx naught into integration of minus infinity to infinity d delta Rx into e raised to power minus beta C delta Rx square into 1 plus beta G delta Rx square plus beta F delta Rx raised to power 4. In the above integral, only beta G delta Rx cube contributes, and hence the integration of minus infinity to infinity d delta Rx into e raised to power minus beta V is approximately equal to e raised to power minus beta V as a function of Rx naught 3 under root of pi divided by 4 into 3g and brackets beta C raised to power minus 5 by 2. So finally, the average value of delta Rx we get is 3g divided by 4c square kBt. The above expression equation shows that as the temperature increases, the crystal expands, since the average of delta Rx is proportional to the temperature. Lindemann melting formula. Let us now determine the melting temperature of a solid. To this end, we will be using quantum concepts. A solid melts because the vibrations of the atoms about the equilibrium positions become too large. Hence, we have calculated the mean square amplitude of vibration, that is delta Rj square average at a certain temperature. We can make a preliminary guess that a solid will melt if delta Rj square is approximately equal to R naught square, that is square of the interatomic spacing. A parameter which can quantify the melting of solid is R, which is equal to average of delta Rj square divided by R naught square. Now, since from our module 2 we have the expression for the vector delta Rj is equal to 1 by root n summation over k lambda, the polarization vector epsilon hat k lambda multiplied by q hat k lambda into e raised to power iota k dot Rj naught. Since delta Rj square then becomes 1 by n summation over k prime lambda lambda prime q hat k lambda and q hat dagger k prime lambda prime into e raised to power iota k minus k prime dot Rj naught into the polarization vector epsilon k lambda dot epsilon k prime lambda prime. Now we will retain only the terms for which k equal to k prime, lambda equal to lambda prime, since other terms for which k not equal to k prime and lambda not equal to lambda prime describe transitions between states with different phonon occupation number nk. So consequently, the average of delta Rj square is equal to 1 by n summation over k and lambda, and then average of q hat dagger and q hat. So what we do now is that we express the average of delta Rj square in terms of the phonon operators. So this implies that average of delta Rj square is equal to h cross divided by 2mn summation over k and lambda divided now 1 by omega k lambda, and then we take the average of a dagger k lambda minus a minus k lambda into a k lambda minus a dagger of minus k lambda. So if you evaluate this expression using the commutation between a and a dagger, then what we get is that the average of delta Rj square is equal to h cross divided by mn summation over k lambda 1 by omega k lambda into brackets average of nk lambda plus half. So you see here that the average of delta Rj square now is expressed in terms of these phonon number operator nk lambda. So delta Rj square average is equal to 1 by mn summation over k lambda average of the energy E k lambda divided by the frequency square. Now the average of n k lambda and average of E k lambda are the average number and average energy of phonons in mode k lambda. This will now help us to write the expression for R, which we had previously defined. So R is equal to summation over k lambda average of E k lambda divided by mn omega square k lambda R naught square. Now what we do is that we will now take the help of this Debye approximation, that is omega k lambda is equal to V lambda multiplied by mod of k. So what we have done here is that we have therefore applied for low temperatures only, taking into account only the 0 point vibrations. So that is R low. So this low basically implies that it's a low temperature result. A summation over k lambda h cross divided by 2mn omega k lambda into R naught square. So replacing this omega k lambda from the Debye approximation gives us the 3 h cross divided by 2mn v lambda R naught square, then summation over k 1 by mod of. So this R low can now be further evaluated, and what we do is that the summation is now replaced by an integral, and the limit of the integral, if you look at it, is from 0 to some cutoff as we had defined earlier, kd. So evaluating this expression, this integral, we get a final expression for R low, which is 3 divided by 8 pi square h cross kd square L cube divided by mn v lambda R naught square. Now we know from our previous modules that n is equal to kd cube divided by 6 pi square, which is equal to 3 divided by 4 pi R naught cube, and theta d, the Debye temperature which we had defined earlier, is equal to h cross v lambda kd divided by kb. So using this we get new modified expression for R low, that is R low now is equal to 0.4 kb into theta d divided by m v lambda square. For high temperatures, using the equipartition of energy, that is average value of ek lambda should be equal to kbt, we have now an expression for the higher limit, that is for R high, which is equal to 1 by 6 h cross square kd square into kBt divided by m theta d square. Now if T is greater than theta d, then we can write down a relation between the melting temperature Tm and theta d as that theta d is equal to square root of 1.6 divided by Rm multiplied by h cross square kb into Tm divided by m multiplied by square of 2.4 divided by R naught, and the entire expression is now in under root, where Rm is a critical value of R for which melting will occur. Now let us analyze that what we have learned from some experimental values. So as we had seen that this melting occurs above a certain critical temperature. So let us see what the experiments say and how it compares with the theory. So this particular table which we show here contains 3 examples, that is lithium, sodium and potassium. So in the case of lithium, as we see here, that the predicted melting temperature is 459 Kelvin while the experimental is 400 Kelvin. Sodium is 370 while the experimental is 160, and potassium is 355 and the experimental is 100. So you can see that in this table that if the temperature is much more than this experimental theta d, that what we have measured, the solid will melt. So this clearly shows that the Lindemann criteria is satisfied by these experiments. So let me again just repeat for clarity that you can see that this melting temperature Tm is higher than this theta d, and if you remember, we had noted down that if the temperature increases above theta d, then the melting will take place. And what is the reason for this? That the temperature increases, the lattice vibration increases. And what happens when the lattice vibration increases? Well, we are deviating from the harmonic approximation. It's no longer harmonic. So an anharmonicity comes in, and as soon as the anharmonicity comes in, the interatomic spacing increases from the equilibrium value tremendously, and hence it is anticipated that the solid will melt. So students, let us summarize what we have learned in this module. First, we have learned that thermal expansion and melting of solids is due to anharmonic effects. Now, well, the anharmonic effects comes into play when, as we had already discussed, that interatomic spacing, when it becomes very large. Well, when does it become very large? The temperature is increasing. It becomes so large that the harmonic approximations breaks down. It's no longer harmonic. So you have to go beyond the quadratic terms in the Taylor series expansion of the potential. Second thing that we learned was the melting of solids is expressed in terms of the Lindemann melting formula. The Lindemann melting formula is basically derived from the fact that the deviation from the harmonic approximation. Remember that. It is closely related to that. The Lindemann melting formula tells us that as temperature rises, the lattice vibrations become large. It becomes large to the extent that it can becomes a couple of times more than the equilibrium spacing between the two atoms, and hence the solid will melt. So remember that before it melts, a thermal expansion takes place, and then when the temperature is so high that the interatomic spacing becomes very large as compared to the equilibrium spacing between two atoms, the solid is said to melt. And this is exactly what the Lindemann melting formula tells us.